Test, test. No. Test, test, test. Oh, it's meeting already?
I will come.
Send email. So sometimes I need you and I don't know you. Okay, test. Test, good, okay. So now it's recording already? Is it recording now? Okay.
I'll love to say that. I still got because it wasn't working.
I like it. Are we supposed to?
Okay, let's see what happens. 9:03, okay.
You guys are, as long as it's like same.
So that's pretty good.
I think.
Yeah, it should be.
I know how to do that.
Okay, good morning, everyone. 10 more seconds to finish up conversations. Okay, wonderful. Are you sitting in teams? Yes? No? That's a different story, but hopefully everyone is, yeah, I know you guys are, okay, that's good. I want you to sit in teams, okay? This will increase your performance, team performance and team dynamics will get to know each other better, so you're gonna produce better reports, okay? All right, today I'm really pleased to have Mr. Josh Loughman with us. He's going to focus about systems dynamics and systems engineering careers. And then he's going to show us two models. One is Enroad, and the other one is Easy Power that I think ASU is doing with the government office. And we will learn a lot of practical examples of how systems dynamics is being used. Okay. So before I give him the floor, I want to introduce him officially. So he's a systems engineer, futurist, and interdisciplinary system scientist. Over his 20 years, he has worked in aerospace, energy, higher education, and climate tech. He is now a principal data scientist at ASU's Resilient Theater, which is this one, right? Right here, right here. I grabbed him from that building. And then a global futures scientist at the Global Futures Lab, and affiliated researcher at the School of Complex Adaptive Systems, and then instructor for the Fulton School of Engineering, our school, and the School of Technology for Public Health. So he wants to take the questions. He can take the questions if you want during this presentation as well. And you can do it at the end as well. But at the end, I will want him like 10, 15 minutes to be able to meet with you guys in person. If you have questions, you can ask. And if he is willing, you can exchange your information, LinkedIn, email, or whatever, if he sees it appropriate. So that I leave to him. And that's pretty much what we're gonna do today, okay? Just one thing, if you're gonna ask questions, I'm recording this session for the ones who are not here, and possibly for my future students as well. So please get the mic. Chinya will bring you the mic. So when you're asking questions, get the mic so the online students of the recording has your voice as well, okay? So please join me welcoming Mr. Josh Loughman. Thank you. Floor is yours.
All right, thank you very much. Thanks for having me. I'm going to do three things in my talk today. The first is I'm going to talk a little bit about myself, just a little bit of an extended biography, a little bit of background to talk about my journey, my path from systems engineering to system dynamics to what I do today. I'm also going to show you two really awesome system dynamics models. One is probably the most sophisticated system dynamics model in the world, and the other one is based on probably the second most sophisticated system dynamics model in the world. So that'll be really interesting. We'll go through some exercises with this tool. The last thing that I'll do is I'll talk a little bit about careers. Career opportunities both in system dynamics and probably more importantly with system dynamics. Careers that aren't directly doing work with system dynamics, but are integrating system dynamics into everyday activities or other kinds of activities. Okay, first, a raise of hands. How many of you have heard of Enroads before? Excellent, great. So brand new introduction to this. Okay, so let me start with the bio. Last summer, I went to a workshop in Japan on AI ethics and society. And all of the speakers who are from Hiroshima University, they gave this really long biographical introduction. And they're doing a 30-minute presentation. And they used 10 of those minutes to talk about like where they grew up and their childhood hobbies. And it was like, what is happening right now? And it was, at first it was a little confusing. And then after a while, I realized this is a really powerful tool for connecting with speakers, even in a very short amount of time. So especially given the context of where you all are and my background, I think it's important for me to talk a little bit about that journey. Okay, so I started out in engineering. I got my degree in aerospace engineering, and I worked in the defense contractor world for 10 years. Doing primarily systems engineering and control systems engineering. How many of you know who Jay Forrester is? Every hand should go up. Okay, so Jay Forrester is the founder of System Dynamics. His background is also in control systems engineering. So I feel like my path has followed a somewhat similar path as Jay. So I spent 10 years in the aerospace business doing systems engineering. And I loved working on satellites. I loved working on rockets. And I started working on business development. I started working in space policy. And it occurred to me that my system boundary kept expanding. What mattered to me at first was the technology, then it was the system, the group of technologies, then it was the business, and then it was the use cases and the customers and the policies around it, the environmental context around it. And so that system boundary just kept expanding. And long story about getting my master's degree in systems engineering at ASU. Some of the same professors you may have, I had in that program. And the company I was at had a very interesting tuition reimbursement program where they would continue to reimburse tuition after a master's degree a little bit every year. And so I said, I'd like to take this class in system dynamics modeling. And they said, system dynamics modeling, that sounds great. Those are all words that we love at this company. Go for it. What they didn't realize was it was really economic modeling, it was social systems modeling, it was all the things that you're getting to know, which was probably not exactly what they thought it was. So I finished a graduate certificate in system dynamics modeling from Worcester Polytechnic Institute. And that really opened up my eyes, really changed my trajectory of what I wanted to work on. And so I came to ASU to teach engineering. This was back in 2015. I taught engineering, both kind of intro to engineering, some systems engineering courses, some modeling courses. And one of the things that I really got involved in at that time was thinking about energy futures, thinking about how the global and the state and the national energy system could, should, may evolve in order to solve climate change, in order to make our lives better, in order to make our bills cheaper, all of those kinds of energy futures. And we did a project that was sponsored by one of the local utilities, Salt River Project, and they loved it. They said, this is great. You showed us a bunch of different pathways to different futures. It'd be great if you could come work for us and read it to us now that you've written it and help us integrate it into our strategy. And so I hadn't really thought about myself as a strategist or as a strategic planner, but they really wanted an in-house futurist. And I said, sure. So I went to SRP for 2 years, did mostly scenario analysis work, some technical analysis, some forecasting, a lot of uncertainty in the future of energy. So there's a lot of both quantitative and qualitative futures needed to be developed for that. A couple of times got to use system dynamics. There was the beginning of the war in Russia and Ukraine. There was some system dynamics that we did to look at different strategy scenarios for the company. But not a whole lot of opportunities to use system dynamics, just a few. And then great opportunity came along, Climate Interactive, which is the small climate tech nonprofit that creates En-ROADS, that improves En-ROADS and runs En-ROADS. They needed a chief technology officer. And so they said, we'd love for you to come be our CTO, our director of modeling and technology, run our modeling team so that we can continue to make En-ROADS better. And for 2 years, I did that. Had a great privilege to work with some of the best system dynamics modelers in the world. Got to lead them in a lot of ways. Also, really cool thing about this company is everyone in this company is trained to deliver the tool. This is really the one thing they make in a workshop like this, in a workshop at the Conference of the Parties, United Nations. So COP28 was in Dubai. And we got to go with this tool and work with the negotiators, work with the delegates from different countries who were trying to decide what the language on global climate policy was going to be. We got to test it with them live with this tool. That's a phenomenal opportunity. Really, gave me the chance to see some of the power of system dynamics modeling in action. The ability to test our mental models, the ability to understand behavior over time. And these are not technical experts. These weren't engineers. These are lawyers mostly, diplomats, right? So being able to communicate with them in a way that they could understand and they could actually visualize how policy might change was really a profound experience for me. So last year, I gave an Enroads presentation at Decision Theater, and they hired me on the spot. They're like, "This is exactly what we need in our life. This is exactly the kind of work that we're planning on doing, and the kind of work that we need to integrate into our current projects, our future projects, and build out a whole new modeling team." So, briefly, Decision Theater, again, right across the hall here. They have really three groups. So there's a data science team, there's a software team, and there's a human-centered design team. And we build models, simulations, and experiences to support decision making. So we'll build a tool. Usually we have a 7-screen environment. It can run on one screen, and I'll show you one of those. We'll build a tool, and it's not a tool necessarily to create an answer. It's not an answering machine. It is a context machine. It's a way for people who are deliberating, people who are having the conversations that lead to the decisions, meet in that space with the tool that we've provided to give them the context to overcome barriers, to check their mental models, to allow them to experiment with different policy ideas or different scenarios, and then ultimately arrive at, we hope, a better decision than they would have without it. So that's where I am today. I think in my bio, I teach some classes too. I teach the data science, analytics, and engineering capstone, master's capstone. I teach class in data science for public health, also developing course on quantitative futures for the School for the Future of Innovation and Society. So it'll be like 5 different schools that I will have taught with at some point. So I get around campus quite a bit. Okay, so before I jump into the second part of my talk, any questions? And feel free to ask questions throughout. Yes, in the back.
Can you repeat
Mike?
this?
Yeah, can we get the mic?
I'm going to grab a coffee while you get the mic. There you go.
I just wanted to know if you could repeat the 3 groups. I think you said data science, software,
And human-centered design.
source.
Yeah, and the human-centered design part is really an important element of what Decision Theater does. Again, there's a lot of groups that will do research, a lot of groups that will build a simulation or build a model, build a tool that provides an answer. But it's really about, are we answering the right question? Are we having a conversation around the right things that people are talking about? So that's where human-centered design comes in. Yeah, other questions? Right.
So how did you end up going from the industry to just education? But also, since this was a nonprofit, do you still work with them, or are you still allowed to work with them, being in
Yeah.
education?
Yeah, 2 great questions. So, how did I make the transition from industry to academia, and then academia to government, government to nonprofit, profit back to academia, and do I still work with them? Okay, so I think the nugget, right? The takeaway is say yes to opportunities more often than you say no to opportunities. So I was in the company, and my mentor was the director of engineering, and he was on the board of the Chandler Gilbert Community College. And they had a intro to engineering instructor who didn't get their visa. And it was like, class starts next week. And they said, do you know somebody that can teach this class? And I happened to be sitting in the room with him. And he said, hey, could you teach an intro to engineering class? It's MATLAB and SolidWorks. I said, yeah, I can teach that. And I hadn't touched SolidWorks in like 10 years. So, but I was, yeah, I could probably figure that out. And so I taught intro to engineering at Chandler Gilbert Community College and fell in love with teaching. And then opportunities came at ASU where I felt confident that I could do that because I had that experience at the community college. In fact, the day that I interviewed for the lecturing position at ASU the first time, what I had also interviewed at a bank, and the bank was really interested in looking at risk modeling using system dynamics. They were going to pay me a lot more money, and I thought, do I really want to work for a bank, or do I want to like teach and like engage with students and people who are doing creative stuff? I'm pretty sure I made the right decision, but I don't know yet. Okay, so then the second question is, do I still work with them? Yes. Sort of, right? They don't pay me anymore, but they have an army of volunteers. So they have almost 1,000 people who have been trained to give this workshop. And they're all over the world. And the training is free. You get your certification as an Enroads climate ambassador, and then you can go and give these presentations. And that pays sometimes. More often it doesn't, but sometimes it does. And I also work closely with them on their new material.
But
So
I'm not gonna pay, so this.
yeah, that's right. This currently is unpaid, right? Just FYI. But they have new material they come out with almost every month. And I consult with them on whether those are good improvements or whether, there's a lot of design iteration on this. I mean, it's a phenomenal interface, which we'll go over a little bit in a moment. It probably doesn't look like any Logic or Vensim or Stella, because it doesn't look like that at all. Great question. Thank you. Any other questions? Okay, so because of that question, I'm gonna say a couple things about En-ROADS that we don't normally talk about in the workshop. But En-ROADS is a fully system dynamics model. And so behind it's tens of thousands of stocks and flows and equations. And it doesn't look like any Logic or Vensim or Stella, and that's because of an open source software tool that was developed by Climate Interactive called SD Everywhere, which you can find on GitHub if you're interested. SD Everywhere will take Vensim code and turn it into a web page, turn it into WebAssembly. So there's this huge system dynamics model in Vensim in the background. They run it through this software to create this website, and the website will run in real time. All right, so we can choose a policy, and you can see those graphs moving, and that's happening in real time on the browser. So there is no server. It's all like I could be on the plane with no Wi-Fi and still experiment with this model. And so it's a incredibly lightweight for such a powerful tool. Okay. So the traditional use case for En-ROADS is to think about what are the pathways, what are our options to achieve climate action, global climate action. How many of you have heard of the Paris Agreement? Yeah, okay. So the Paris Agreement in 2015 said, as a world, we should strive to be well below 2 degrees Celsius, above the pre-industrial average mean surface temperature. That's what this number is right here, 3.3. That's the trajectory we're on according to the En-ROADS model. So we want to get that number. This is why it's the big number in the upper right-hand corner. That's the thing you should be focused on. We want to get that number, if we're Paris 2015, well below 2, aiming for 1.5. Right, 1.5 is kind of the stretch goal. Now there's a whole lot of ways we can do that. And that's represented by these 19 sliders here at the bottom. Each of those sliders is connected to at least one policy. Some of them are connected to multiple policies. And these are the things that we have at our disposal to address climate change. What's something you notice about these sliders? Anything?
You go from like low, medium to high.
Low, medium, and high. Okay. What else? If it's just low, medium, and high, how do I know what's low, what's high? Say I want to tax or subsidize bioenergy. What's highly taxed bioenergy mean? Yes, sir.
Oh, I was just gonna say they all have. I was just gonna say they all have like a status quo baseline.
Yeah.
Where we're starting from.
So they're all starting with a status quo, right? So what is current policies? What counts as current policies? This is a huge debate in the modeling world, right? Do we say, oh, well, this country committed to cutting greenhouse gases in 2030? Is that a current policy? Some people say it is. En-ROADS doesn't take commitments as current policies. If there's a law that says they're going to do it, that's a current policy. If it's just a stated commitment, it's not a current policy. It's represented by the sliders, right? You can say, okay, well, if they're going to do that, then we can say, well, they are going to tax coal. We can represent that as a slider, actually. Okay. High, medium, and low is also not numerical, right? There are no numbers. What's high? Is 1,000 high? Is 100 high? Do you know? Do you need to know? The first point of this interface, and again, they anguish over this interface. The first point of the interface is not so much about levels. It's about polarity, which you are all learning about with your loops, right? So what happens if I raise carbon price? What happens if I lower carbon price? What happens if I increase subsidies for renewables? These are all sort of directionality points. How are these things changing if I give it this direction or that direction? Now, if I care about what specific carbon price I want to look at, I can click, I did that kind of fast. I can click on these 3 dots and you can see each of the sliders has these 3 dots. I can click here and I can see status quo right now in the world is $5 a ton of CO2. That's the global average. I can set it at some other number, like say 85. I can put in specific numbers at this part of the interface. And when I close this part of the interface, it's still there. It's now just that polarity shift. Okay. So the idea here is not only can I get polarity questions answered, I can also get specific values. Okay. So again, the use case is how do we get to 2? How many of you are working on a project on energy, climate, the environment? Nobody. Okay, good. Well, not good. You should work on climate change. It's a big deal. Okay, but how many of you have ever heard of a solution to climate change? Any solution? Any idea for solving that problem? Yes.
Cutting greenhouse emissions.
Okay, from what?
Cows, also like industry, like factories stuff.
Great. So that is the answer, right? Is this graph on the right is the greenhouse gas net emissions. Right? This is the problem. This is where climate change comes from. All we have to do is bend that curve down, and you can see we've got the baseline and we've got the current scenario, and we can look at different policies and how those different policies do that. Okay. So you mentioned cows. All right, so that's a policy. What's one other policy that we could do? You can look at the screen. The answers are on the board. Yeah, more solar panels, okay?
Or like focusing more on renewable energy.
Renewable energy, okay? Solar, renewable, and agriculture. One more. Deforestation. Okay, why is deforestation important? What does deforestation do for us? Sorry, I can't hear you over the drilling. Everyone else hears the drilling, right? Yeah, it's not just my tinnitus. Okay,
You're
good.
gonna stop. You're gonna stop. I guess more trees we cut down. That's far.
Right. Okay, so let's take a look at there's so many graphs here. Let's take a look at this graph. All right. This is a graph, behavior over time from the beginning of this century to the end of this century. Somebody tell me what's happening in this graph.
How many trees are up there?
So these are all different. The gold part is the number of trees that are deforested. Deforested means permanently cut down. Degradation is I cut it down, but I planted some new ones. So and these are all mature forests. So these are the old growth. These are the Amazon, the Canadian forests. Yes.
So is the y-axis here telling us how many million hectares we have per year cut down, or how many we have remaining?
Cut down.
Okay, got it.
So the good news is it's going down over time a little, right? Mostly, I mean, degradation is not, right? These are all pretty stable, maybe growing even a little bit. Deforestation is not going down that much. And it's not because we ran out of old growth forests, although that was a thought I had at one point. Okay, so if I institute a policy to save the rainforest, right, to save the old growth forests, what do we think is going to happen with this graph? If this is the rate of deforestation and forest degradation for mature forests, and we're going to institute a policy to save them, it's going to go down. Okay, I saw some people motioning down. Okay, so we're going to protect old growth forests. Okay, now we can look at the window. We can even play that back. Okay, what do we notice?
Down.
They all came down. Wait, did they all come down?
Fire went up.
Fire went up. We protected forests, and forest fires went up. Why?
Higher densities.
Okay. Higher density forests, that's part of it. Yeah. More forests, right? We protected, we didn't cut them down, so there's more to burn. And why? And this isn't all fires, right? This is just fires from climate change. It's the fires that we can give some attribution to climate change. So, did we solve climate change? No. In fact, we about 1/10 of a degree down. Okay, so we didn't do much about climate change by protecting the old forest. We did a little bit, but because of that, the forest fires are still a problem. Now, it's not as big a problem as the whole deforestation project was. Okay, so that's good. Okay, so I want to move a little quickly through a couple of other policies. We talked about renewables, so I'm going to look at that one. So this graph represents the stocks of the different forms of energy that we use. This is essentially the grid mix. Where's the electricity coming from when I plug something in to my outlet, or when I plug my electric vehicle into its charger? So where's all the energy coming from? Most of it. Renewables, right? And not only that, like, we're here. Wow, we're putting a lot of solar panels out into the world, and a lot of wind turbines, and a lot of maybe some hydroelectric and geothermal. What else do we notice? What else is surprising maybe about this graph?
Coal increases over time.
Yeah, so coal has this rebound in the second half of the century. Okay, what else do we notice? That's a great observation.
Oil is barely visible.
We don't use that much oil at all for electricity generation, right? There's a few island nations that use diesel generators, like Puerto Rico, the U.S. Virgin Islands. We actually just had the governor of the U.S. Virgin Islands in yesterday to talk about their energy system, their diesel generators, but it's very small, global amount. Another thing that I think surprises people about this graph is how little a role nuclear plays, even though at least this year it has been a very hot topic. So we can experiment with things like what would happen if we were to subsidize nuclear. Okay, a little bit more growth, but actually still a pretty small piece of the puzzle. And if we do renewables too, renewables and nuclear really compete with each other more than add together. So these are the kinds of feedback loops that we have integrated into this model. Feedback loops that connect the energy supply with the energy demand, with the economic uses, and the climate system. Okay, so I want to get to the next model. So I'm going to try and go a little faster. What's one other thing that we can do? So we've talked about adding renewables. Is there something we could subtract? We could subtract coal. Okay, so let's take a look at, I want to take a look at, this is coal, and this is this one, natural gas. So if I tax coal, primary energy demand, this graph on the left should go down, right? What do you think is going to happen in natural gas? Going to go up. Why would it go up? Yeah, so this is a phenomenon. You may have heard about this in your studies. This is a phenomenon called squeezing the balloon, right? You tried to solve a problem, so you squeezed the part of the balloon that you're trying to solve the problem. What happens when you squeeze a balloon? Not that it blows up in your face. The other thing it does, it gets bigger somewhere else, right? The problem comes back in a different way. So when I pull the slider to tax coal, coal's going to go down, and gas is going to go up. Gas is compensating for the more expensive coal. That's actually what we're seeing today in this state and the Southwest and a lot of other countries too. Coal is not cheap right now. It used to be historically very cheap, and it's now more expensive. So some of it's getting replaced with renewables, some of it's getting replaced with other things, but a lot of it is getting replaced with natural gas. So one of the sort of cheat codes in this model is carbon price. Why is carbon price an effective solution to that? Yeah.
Make a high carbon polluter expensive. People are more likely to then go into other industries that don't cause.
That's right. Because it affects both of these, right? Coal is dirtier than natural gas. So coal is going to get affected more, but natural gas is going to get affected too. And the things that won't are hydro and geothermal and solar and wind and nuclear. So if we pull the carbon price, we should see, I mean, coal gets decimated. Coal is done by 2080. And if we really want to get creative, there's a lot of advanced policies we can go into here. We could go in and we can say, we're actually going to just reduce all coal utilization. And we're going to make that, we're going to let that go. We're going to accelerate the retirement of existing coal power plants too. So we're killing coal in this model. Okay, does that solve climate change? Did we do it? Is Paris happy? No, we're still at 2.5. Okay, but we forgot about methane. All right, so let's go to methane and we'll go here to greenhouse gases. And I want to look at this one. Okay, so this is a graph of all the greenhouse gas emissions over time. We have greenhouse gases come from land use. We have these fossil fuel CO2 that we've been obviously taking a big chunk out of. We also have the gold, which is F gases. What's it? Anybody know what an F gas is? Fluorinated gas. So CFCs, SF6, HCFCs are man-made gases that were used as solvents and coolants and fire suppressants They're used in a lot of equipment like air conditioning systems and refrigerators. So you've heard of Freon. Freon is an F gas. Now, normally you run it in a closed loop, it leaks a little bit. And we noticed back in the like 80s that there was this big hole in the ozone layer because a lot of these gases are ozone depleting substances. And we said, this is terrible. Like, we need the ozone to live. If we destroy the ozone layer, it's going to be really, really bad. So the world, decided with the Montreal Protocol and later the Kigali Agreement to ban the production of certain fluorinated gases, ozone depleting substances. Some of them aren't ozone depleting substances, but they are still greenhouse gases. So those are growing over time because the economy is growing over time. We want more air conditioning units. We want more refrigerators. We want more transformers on our electrical grid that uses SF6. And then we also have CH4, that's the methane from the cows and the rice paddies and other agricultural practices that create methane. And we have N2O, which is from fertilizer primarily. Okay, those are not going down. Those are going up because of the economic growth that we have. So can we do something about that? Well, how could we reduce methane from cows? What's a policy or an idea? And I'll put the answers on the screen so you can. We could all go vegan. I love the faces I got when I said that. Okay, so we can't actually in this model all go vegan because that would be a sort of magical thinking that's just not realistic. We can reduce the amount of food from animals. That's this slider right here. And that should reduce methane emissions. Okay, so we're gonna look at this one. And actually, I want to pull up this other methane. So this one is just methane, and this is from, this is just from energy though. This one. There's like 150 graphs, so they get used up. All right, so we took a lot of methane. Methane comes from natural gas. We did a lot of work on natural gas. That's great. Agriculture is huge, and then we have some from waste. And industry is like, doesn't even register on here. Okay, so we can go vegan, right? How much can we go vegan? So currently the average or like a conventional estimate for a Western diet is about 30% of your calories come from animal products. As the world increases in its economic development, that is the level that it approaches. Okay, what should we? And again, this isn't really a policy. This is an experiment of social change. How much do you think we could reduce by? 20%. Okay, so let's take a look at 20%. It goes down to 10, but 20 is pretty good. And we can look at, we can replay that and see how much does that do. Not too much. Let's see, it goes from 2.52 to 2.48. That's like a rounding error in the total amount of climate change that we're dealing with. So veganism itself is probably not the answer, or an increasing amount of that. Now we can also do other things like we saw a lot in industry or in waste. We can reduce that. We can also reduce. We can increase our best practices when it comes to how we manage livestock, how we manage cows, how we manage horses and goats and other animals. And so when we do that, we actually get pretty close. So we have a very high carbon price. We killed coal. We subsidized nuclear and renewables. We saved the rainforests. We, most of us, half of us started, experimenting with veganism. And we did a high reduction in waste and leakage. And we're at 2.1 degrees. That's pretty good. One more idea to get us over the finish line.
efficiency.
Energy efficiency, what were you gonna say?
Carbon dioxide removal.
Carbon dioxide removal. Okay, let's do them both. All right, so we're gonna increase energy efficiency in transportation. Let's look at this graph. It's actually my favorite graph in this whole thing. Yep, this one. They changed the colors a little bit. I don't really care for it, but okay. Okay, so this is the buildings and industry consumption by end use. So you can see we're not using hydrogen a lot, but we've electrified a lot of buildings. We have some buildings that are still using fuel. We still are driving almost the same number of internal combustion engine car miles. It's not just cars, it's planes and ships and other things, trains and stuff as well. But we have quite a bit of electric transportation. So that's great. Okay, so we're going to look at this graph in a moment. We're going to increase the energy efficiency of transportation. Doesn't change much. Energy efficiency of buildings, however, changes a lot. So buildings use a lot of energy, a lot of heat. There was actually this debate just recently. Somebody said, how does anybody live in Phoenix? It's so hot, your air conditioning bills must be crazy. And I said, you live in Chicago. Like, you're in a blizzard at this moment. What's your heating bill like? And nobody's ever said nobody should live in Chicago because it's impossible to live there without heat. Well, they say it's impossible to live here without air conditioning, which is true. But that's a reason why I'm still here. Anyway, I'm getting on the soapbox. So energy efficiency, wow, okay, 2, and then we're going to do some carbon dioxide removal. We could do that with planting trees, and we can do it with direct air capture technology being developed here at ASU. All right, so if we deploy those kinds of technologies and we plant a whole bunch of trees, hey, we're down to 1.8 degrees. We solved climate change. Let's give ourselves a round of applause. Now, what is the point of the model, right? Part of it is to experiment with these different mental models, experiment with these different policy choices. Part of it is also just to realize we can still do it. I think there's a lot of defeatism, a lot of fatalism out there in the climate world. And so this isn't going to be easy to do all that, but it's not impossible. We have hope, right? We have ideas that we could be deploying. Questions? Yes.
Not really specifically climate change, but technically climate change is production of clothes and consumerism.
Reduction of what?
Just wait for the mic. Your voice is not going to.
Yeah, let's do the mic.
Consumer, people overconsume, and it takes build up.
Yeah.
I mean, I'm in a cloud.
Say it again.
I was thinking about. I don't want to be too loud. About overconsumption, clothes and making clothes and things like that. Takes greenhouse gases to do that, and I'm in a fashion club, so I get that there's so much overconsumption. People buy new all the time. Then, that does cause a lot of greenhouse gas production and climate change majorly, really bad.
Yeah, it's a really interesting question, and one that is not directly addressed in En-ROADS. We've been talking a lot with groups that do circular economy and degrowth models and sort of alternate economic models on how to kind of factor that into some of this discussion, possibly even factoring it in directly into the model. One thing I will say that's related is there is a cost to climate change. It's not just bad for us. It's not just bad for our health. It's not just bad for the coral reefs or whatever. It's bad for our economy. And one of the things that just a couple of years ago we implemented in this was a damage function. So it's this big feedback loop that says as the climate gets hotter, your economic growth is going to go down. And so we could calculate what is the missing economic value from climate change. And that's what the dashed line is. The dashed line is what would our economy continue to grow like if we didn't have climate change? And because of our actions are actually pretty close, right? Because we're at 1.8. But you can see the baseline is much worse. Yeah.
Does that take into account the short-term costs of subsidies and other things like that, which will cost, or stifling third world or emerging market development by taking away easy energy sources?
Terrific question. The question was, does the economic growth take into account the short-term costs of subsidies or the cost of taxes, or the missed opportunity for development with fossil fuels or with other technologies? And the answer is no, not directly. It's actually one of the big improvements that I think En-ROADS should undertake. It's two parts. One is the economic costs of these policies. They do have the if you look at this, they have an estimate of like the costs of subsidies and the costs of tax, like the government accounting, if you will, not the economic accounting. The other feedback that I think is really important here is, and it's kind of a touchy subject in global systems modeling, which is how should we think about population? Nobody said we should reduce population, which is great. It does come up in almost every one of my workshops, and it is a slider, but it's not really a policy slider because it's not really a policy that is taken seriously at the moment, and it also doesn't really have that big of an impact, which is interesting to explore. So some of the mental models that we test with this is, you think this is going to be a good idea, let's go find out. Oh, it's not. Okay, let's move on. And that's where population sits. But there are feedbacks that are not in this population model. So as economic growth goes up, population growth tends to go down. And a lot of recent research on economics and demographics have borne that out. That's something that I think this model would benefit a lot from. Yeah, Ollie.
Oh yeah. So this reminded me of George Buck's quote, right? All models are wrong, some are useful. So this is wrong but useful.
Yeah.
But from a practical perspective, I'm really curious about when you present this in the, climate summits and these meetings, and you went to workshops. What are top three discussions that came around, like frequently, all the time, in every workshop? Like, where is the geography here? Like, my country is not producing as much, I'm not guilty and stuff. So what are like top three things that comes around all the time?
So loss and damage is one that came up a lot, which is if there are economic damages, someone's responsible for those damages, right? In a legal sense, they could be. Who's responsible, and so who should be paying into the pot to make reparations to the countries that are damaged by it? So that is something that comes up in these conversations. This model doesn't directly address that, but it does create that context for that conversation, which is great. Another one that comes up a lot is technology. So I gave a presentation. It was actually the opening keynote for this energy conference in New Mexico late last year, and they were really interested in technologies. They wanted to know, what about hydrogen? What about carbon capture and storage? What about advanced nuclear, right? And what are the conditions? Direct air capture was another one. What are the conditions under which those technologies make a difference? Because they don't make a difference in the status quo context. They're too expensive. They're too slow. Because they're slow, they're not benefiting from a learning curve, which we didn't talk a lot about here. But the more you build something, the better you get at it. So if you're only building a little bit of a thing, you never get better at it. It never gets cheaper. You never build more. So there's this reinforcing feedback loop of learning by doing, that if you highly subsidize, and this is really like been the success of renewable energy, right? Solar energy is one of the cheapest forms of energy on Earth, because somebody, federal government primarily, and the EU government, subsidized solar significantly so that a lot got built, and now we know how to build it cheap. Now we don't need the subsidies. The subsidies are still nice. We should still have them, but that's another soapbox. Yeah.
Given all of these different variables, what did you find if we were going to do like a Pareto analysis of the variables? What are your top two? What's your 20%?
So that's a fantastic question. The question is like, what is the Pareto frontier, right? What is the right combination of these to be perfect, right? And there's a whole lot to say about that. One is, my preference is not necessarily the same as someone else's preference. I could show you sort of my preferred combination. I could do it in like 10 seconds because I've done it a million times. But That's my preference, right? So I like renewable energy. I don't like fossil fuels. I don't believe that direct air capture is going to be a significant player. I think there are limits to what we can do on agriculture and deforestation and other things, right? So those are kind of my ideas. But one thing that happened that's super interesting related to this is we collaborated with a consulting company that was building AI, and they used an AI tool to basically run this model a million times and under certain parameters find what was useful, right? Find what were the feasible scenarios within that design space. And one thing that it did that I've never seen a person do is it tinkered with the timing. So if you go into the advanced views, I can say, oh, I'm going to have this coal subsidy. And I could stop that coal subsidy in 2040 if I want. And I could start it in 2030. Like the timings could be changed. Nobody, I mean, very, very infrequently does someone ever do that even once. But the AI was like, it's a slider. I'm going to slide it. And it found this really interesting set of sequences in the policies that kind of like was really surprising and very, very interesting because of that Pareto, that concept of like an optimality where it basically said, hey, coal's really bad for the environment, so let's tax coal, but let's subsidize natural gas. We're not just going to squeeze the balloon, we're going to inflate the balloon for natural gas for like 20 years. Then we're going to kill natural gas because that's when renewables really are able to take off. So it was like natural gas as a bridge fuel is a concept people talk about, and the AI like discovered it in this sequencing, which was super fascinating. Should write a paper on that now that I think of it. Yeah.
Are you gonna eventually add in a slider about the energy use and like? Are you eventually gonna add in a slider for like the energy and water usage of AI?
Oh, this is a great question. So the question is about data centers and AI and the land use, water use, energy use. So that is actually a project that they are working on right now. And what I'll do, because I know I'm running out of time, is I'm going to show you this model. This is an Arizona model. And so over the last year or so, we've been working with the governor's office and a number of other stakeholders. Now this is a 7-screen model that runs in the decision theater. And in the background is, like I said, the second most complex, second most sophisticated system dynamics model. It's called the Energy Policy Simulator. And they have state models. So this is just Arizona. And we can create similar, we can use similar kind of sliders to say, all right, I'm gonna choose a scenario, call it a fast energy transition. And then I go to the second screen. It's all like 7 screens, but it's all one long screen in this case. And this is like, how would we do this in Arizona, right? With the kind of demand for energy that we're gonna have from advanced manufacturing, from electric vehicles, and from data centers, AI. So we're gonna need to build a whole lot of solar in between the years 2031 and 2035. And we're probably gonna need to boost some natural gas. That's in this sort of cost-efficient scenario. But we can look at new technology scenarios where we're looking at small modular reactors, we're looking at carbon capture and storage, we're looking at hydrogen, both from an energy generation perspective, but also from an energy storage perspective, because hydrogen can be stored for long periods of time. I'm moving through this one super fast. So on the third screen, we've got, this is what the energy system for the state looks like as it grows over time. These are some of the outputs: water use from energy, which is what the water used for data centers is used for, as cooling. Economic and workforce impacts, climate impacts, health impacts. The next one is looking kind of specifically at a problem we have in Arizona, which is extreme heat. So looking at a peak summer day in 2050, this is what the dispatch of energy would look like and where all of the different sources of that energy are coming from. The green is renewables, because that's when the sun is shining and the wind is blowing. but that doesn't happen all night long. So how do we get energy at night? Well, we got to turn the gas generators back on, or we got to use energy storage, or we got to like. This is actually pretty fascinating. The dark green is hydro. So, Salt River Project has a series of dams out in the Superstition Mountains. They can pump water from the downhill dam uphill when it's sunny, when electricity is cheap. And then in the evening, when demand is still high, but the sun goes down, they can let it back through and get that energy back, minus some losses, obviously. So that's part of this. The other question is, where will we put that? So one of the first questions we asked was, there was this interest in small modular nuclear reactors, about 250 megawatts. It's like, okay, we're going to need 20 gigawatts of generation over the next 25 years. That's 80 small modular nuclear reactors. Where are you going to put 80 nuclear reactors? We have 3 in the state of Arizona right now. Where are you going to put 80? And they're like, oh, that's hadn't thought about that. And the technology doesn't even exist yet. And even if you talk to the most ambitious, we had the CTO of a SMR startup a couple of weeks ago come into the Decision Theater to look at this. And he's like, 2040 is maybe the earliest. Well, okay, 2040. So if we go back here, okay, so that means these orange pucks are all wrong because they won't exist. But this was ambitious. This was advancing. So if all of that is here, you still have to generate all this electricity somehow. So you're not even going to get to 80. You're going to do something else. Okay, so that's the dispatch curve and the location, and then we have a compare screen. We also have this blank screen is where we're putting in our transmission model that we're building now. So you put it onto the map, it connects to the transmission grid, and it tells you, do you need to upgrade this transmission line, or is there enough capacity to run it? Okay. I think I went over time, so I'm gonna pause there and see if there's any questions. I'd love to talk if people have questions about careers in this space, particularly where I think there's opportunity to use system dynamics in other careers. So for instance, one of the areas that I was actually really surprised to see so much system dynamics is in consulting. We worked with, one of my system dynamics professors, the question came up, when is the right time to know when you can consult with system dynamics? And his answer was today. That's how you get practice. That's how you get experience, is by taking what you know, even if it's a little bit, and putting it to work and learning as you grow. Found a lot of consulting companies. It's not all consultants know how to use system dynamics, but the ones that do tend to be very successful. They have a way of thinking about things that's more systematic and rigorous and powerful in a lot of ways. Okay, so questions, thoughts? Yeah, sure.
Where I wait for the mic.
Yeah, wait for the mic. The kids tuning in at home.
So my question, I guess it's kind of like 2 in 1, but it's when seeing you go through the whole model and the simulation of the different policies, I saw that many of them, you would think that they would have a bigger impact, and they didn't really have any, or if at all. And that really got me thinking, how do you this is like the 2 questions. How do you go through a process where you go through getting a situation as complex as that, but you still make it still with enough complexity that you can see those changes? But also, how do you go about thinking when you're doing in that process to kind of like see that and be like, oh, I have to add this feedback loop and stuff like that?
Yeah, this is a fantastic question. It's really gets to the core of like why we do system dynamics, how we do system dynamics. What are we using it for? Right? Are we testing? Are we trying to predict the future, or are we trying to test a mental model? And so, for instance, a lot of the if I go back to this real quick, and I'm just going to reset everything, and I say, okay, what about new zero carbon? That's fusion, right? What happens if I get a whole lot of fusion? Nothing, very little, right? It tests that, well, all we need is that free energy from fusion, and it'll save us, it'll solve all our problems, but it won't, right? And understanding the reasons why. Okay, so then the question is, why did we model it if it didn't really have that much of an impact? And it's because when we talk to people, we hear that mental model. They say, well, once we have fusion, well, there'll be nothing to worry about. Like, okay, well, that's a testable mental model. And sometimes the negative is still an important. And one of the modelers for Enroads, this guy Scoop Jones, who's one of the best modelers in the world, he has this rule, right, called Scoop's rule, where if you have something that you're trying to test a negative, you need to make the assumptions as generous as possible. And when you're trying to test the positive, you need to make the assumptions as constrained as possible. Because you have to be able to say, even under these conditions, this works. Or even if you have magical thinking, this will not work. You can't say, well, under these restricted conditions, it does work. Because then somebody says, well, yeah, because you restricted the conditions. So it's a philosophy of test that we employ. Yeah, fantastic question. More questions, more thoughts. Yes, sir.
So I know that Enroads is for like a climate simulator. Do you know of any such simulators for industries, like suppose like different type of industries that come together, and how does it impact the global economics, something like that? Do you know?
Yeah, so there are, I mean, system dynamics is not restricted to really any domain. Any domain where you have stocks and flows that change over time is appropriate for system dynamics. There is, I can tell you a little bit about the work we're doing. So we're doing work on a wide variety of projects using system dynamics. One of them is transportation modeling, looking at the impacts of certain counties in Arizona and how certain investments in different kinds of transportation lead to systemic change, positive and negative. We're looking at Arizona's healthcare system and how there's certain measures that groups use to sort of rank the states, right? And one of the interesting problems with this ranking system is there are these interfering feedback loops that they hadn't thought about. So one is Arizona ranks really, really poorly in insurance, right? The number of people insured in the state of Arizona is like one of the lowest in the country. But we score really well on people who aren't sick seeking care. And I'm like, well, I can tell you why, because they don't have insurance. If they had insurance, they'd probably there'd be a higher preponderance of people seeking care that didn't need it. But they're not going to risk the cost if they don't have insurance. So if you increase this thing, you're probably going to see an increase in this, a compensating feedback. And so these are the kinds of things that system dynamics allows us to model and study and explore that these makers of these metrics aren't thinking about. We're also looking at technology roadmaps, innovation ecosystems, water, as well as energy. So all kinds of systems. Yeah. And that's just across the hall. All right, I think I have time for two more questions. Two quick ones.
So one of the questions I had was just regarding system thinking in general. What was like the one thing that made you kind of think in a systems engineer's perspective, like think from the perspective of systems engineer rather than just being like an aerospace engineer, for example.
So this is a difficult question for me to answer because so when I was a freshman in college, I went to Georgia Tech for 1 year, and I did a project there. It was a AI design competition, and we did really well. We had a really great team, and the experience of aerospace design is so much like systems engineering, where my team lead at the time was like, aerospace is a natural fit for systems engineering because, and no offense to mechanical engineers make landing gear, aerospace engineers make airplanes, right? They have to think about all of the pieces that are connected that still have to function and complete some kind of mission. And that's true for landing gear too, but it's different. It's a different scale. And so the idea of design and systems has always been sort of deep within my practice as an engineer. Yeah. All right, one more quick question. And then I think we've got some minutes. People can ask me the quiet questions.
How would you like present this, or how would you like if someone asked for the results of this model, how would you show this?
So you can share your scenario here. So this is free, right? It's enroads.org. You can share it. You can post it on Twitter, right? I think there's all these. There's also a actions and outcomes. So this is, of course, we reset it. But this is all the things you did in one snapshot. And this is actually where we found that interesting work that Cognizant, or the consulting company that we work with, had done, because it was this huge list. And we're like, why are they tinkering with the dates? That's weird. And then we look and it's like, oh, there's like just dozens of these little sequencing things that were really interesting. Yeah. Okay. Thank you very much for listening to me talk. I'm around if people want to chat. With the microphone.
Idea about
That is a question on the
I've got some.
input that. Oh, you are.